like the skill set, the interference problems like this, two source interference problems, all you have to have is the sources have to put out the same frequency of light, and then they also have to be in phase. If they're out of phase, why that changes things a little bit. So we'll assume that they are the same frequency and that they're in phase, and in phase means that they're moving out at the same time and moving in at the same time. Yeah? Remember we messed with that a little bit? Like we had that thing on there and we put different angles in there and it was like a little bit different, right? But let's assume that these guys are in phase. The rule is that, of course, if the difference in distance is an integer number of wavelengths, then it's constructive. And if it's got a remainder of a half, if you divide the difference in distance by the wavelength and get something 0.5, then it's destructive interference, right? Now, what I'm going to do now is I'm going to turn the laser on, which I've already done, and I'm going to put this up here, and I'm going to send it through. There's a couple slits. And what that does is it divides, there we go. It divides the laser beam into, okay, hold on. There we go. It makes it go two ways simultaneously. Right, so the laser light is shining on these slits. So this is presumably the width of the laser beam, right? It's got some width, right? So it strikes slit 1 and slit 2. Light comes out of those slits simultaneously. It's, of course, the laser is monochromatic. It's also coherent, which means all the peaks line up with all the other peaks, all the troughs line up with all the other troughs, right? You have to have both those things. It has to all be all one color, and it has to be coherent. It has to all be cresting and troughing at the same time, so that these speakers, they're like light speakers, right, are moving in and out at the same time. Only it's an electric field, so it's different, right? And then the notion is that if you're at some point on this screen, you're a different distance from this than you are from that, yes? So the two slits become like the two speakers in the room. Remember when we walked around, we plugged one ear, and we could hear loud, soft as we walked around? Do you remember that? Yeah. So we should get, with light, bright, dark, and indeed, if I strike this key there, you can see, there it is, right? There's a central bright dot. That's the dot that is the same distance from both slits, right? So if you drew a line, these slits are incredibly close together, and if you drew with something like took string from one slit to the next slit, like I see the forensic kids doing, right, in the stuff out in the hall, right? If you drew string there, that center dot would be exactly the same distance from both slits, right? The next bright dot is one wavelength closer to the slit on that side than the other slit. The next bright dot is 2 wavelengths closer to the slit on this side than that one, right? The first dark spot is, I believe, half a wavelength closer to this slit. Yeah. Okay. So that's what's going on. And I'm just bringing this up again because I know you've seen this, because this is, for the wave theory people, this is definitive proof that light can act as a wave. Yeah? And then later on we're going to encounter actual evidence that it acts like a particle. And then, what is light? Well, it's a wavicle. It's a parv. It's both. It can do both, and so therefore it's not something exactly like an ocean wave, and it's not something exactly like a baseball, right? It's light, right? All right. So anyway, that's really all. That's all the farther we need to go with that, because it's much more fun to talk about polarization. Okay, so polarization, yeah, in fact it is.